molecule. Simple molecule is there in front of you, ethyl bromide. As I told you, what we are going to look at, how many peaks are there, what are the chemical shift, and what is the splitting pattern, and what is the intensity. So here we have one peak and you have a second peak. Now you will not call this as a three peaks because now you have understood what is splitting, how the splitting takes place, and why the splitting takes place. Once you understand that, then you know there are only two types of proton in methyl bromide. So I am going to see two peaks. But these two peaks will not be smooth because of the coupling. So A, you can see that A has a B neighboring proton. There are two neighboring protons. So 2 plus 1, 3 lines will be observed and it will be appearing as triplet. Whereas B has 3 neighboring protons. So 3 plus 1, 4 lines will be observed. It will look as a cottage. So CH2 will be quartet, CH3 will be triplet. So you can see here 1 is to 2 is to 1 and 1 is to 3 is to 3 is to 1 is the intensity ratio. Now this peak height has nothing to do with this intensity ratio 1 is to 3 is to 3 is to 1 or 1 is to 2 is to 1. What is important that this peak height is greater than this peak height. Integration now. Okay. So integration of obviously A type of proton will be more than B because there are three equivalent protons, whereas in B there are only two equivalent protons. So you can see the height of A is greater than B because intensity is higher because uh, number of equivalent protons are more. And splitting is ratio is 1 is to 2 is to 1 and 1 is to 3 is to 3 is to 1. So the peak height is little bit decreased over here as compared to this because of the equivalent protons. Nothing to do with the intensities, okay? And let's see the chemical shift. Now out of these two protons, CH2 is your primary proton, primary carbon attached proton, which is next to Br, which is electron withdrawing. So CH2 will be more deshielded as compared to CH3. So you can see CH3 is beta with respect to Br, CH2 is alpha with respect to Br. The values are approximately 3.4, 3.5 for CH2, whereas 1.5 to 1.6 is the value for your CH3. So both are de-shielded because of the presence of electron withdrawing Br. So this is how we'll get the information about the molecule from a simple spectra, NMR spectra, PMR spectra. But what you will find that splitting is not only decided by number of bonds present, but along with that, there are certain other things also which are responsible for splitting. And what you will find, there are two types of splitting observed. One is called the first order splitting, and other is called as a second order splitting. Just now we spoke about first order splitting, where simple n plus 1 will be applicable, and you can find out the splitting patterns for vicinal coupling, okay? For protons with vicinal coupling. Even for geminal also you can find out, but mostly it is used for vicinal. Now, what is this first order and second order coupling? Now, first order and second order coupling is decided by two things. One, what is the chemical shift difference between the two protons? And what is the coupling constant between two protons? If the chemical shift difference is very high, then always first order coupling will be observed. But if the chemical shift difference is very less and delta mu by J is less than 10 hertz. Delta mu by J means what? Delta mu is the chemical shift in hertz and J is obviously coupling constant. If that ratio is less than 10, then only you'll see the second order splitting. Otherwise, you'll always see first order splitting. And first order splitting, just count the number of neighboring protons, add 1, and that will give you the splitting pattern of the molecule. But if you have a olefinic system or an aromatic system or highly conjugated system, then what you'll find that spectra becomes a bit complicated. Before we understand this complication, Let us understand again types of protons. Some protons are called as a homotopic, some of them are called enantiotopic, and some of them are called as a distereotopic. Now, how do I distinguish between homo, enantio, and diastereotopic protons? And how it is useful for in NMR? So what you find that in NMR, PMR, homotopic and enantiotopic protons cannot be distinguished, but we can distinguish between distereotopic protons. The chemical shift value for homotopic and enantiotopic will be same, but for diastereotopic protons, stereotopic protons, it will be different. Let's see, how do I find out whether the protons are related to each other as homotopic, enantiotopic, or distereotopic. Let us take one what you can say, uh, the procedure to find out whether they are enantiotopic or homotopic or diastereotopic. Let us try and understand that. Say you have a molecule over here. Let's take ethane molecule. What do you have to do? Let's say I want to find out the relation between the red and the blue hydrogen. Okay, or you can find out between this hydrogen and this hydrogen. So for the time being, I will consider these two. What you have to do? Replace one of the proton which you want to find out the relation by some other group, some X, Y, Z. Let's say here we are saying D. I have replaced your blue by D and I am getting this molecule. Okay? And same thing you will do with the other proton where you want to find out the relation. So red H is replaced by D and I'll get this compound. Okay. Now what you have to find out, what is the relation between this compound, sorry, between this compound and, sorry. So what is the relation between this compound and this compound after replacement of hydrogen by some arbitrary group, let's say over here D. What we'll find, this and this compound, they are same, they have no difference between them. Everything is same. If you take the spectra, it will also be matching. If that is so, then these two protons are called as a homotopic protons. They are equivalent in all respect. We cannot distinguish between these two protons. Then those two protons will be called as homotopic protons. Obviously, homotopic protons cannot be distinguished in PMR. They will appear as a single peak. Same means they are same chemical shift, so they will be together. Their peak will be same. This is about homotopic. Now let us try to understand the enantiotropic protons. Now, again, we have these two protons. This is the system where I can replace a red hydrogen by D and get, sorry, blue hydrogen by D and get this. Or I can replace a red hydrogen and I will get this. Now, when I replace, what I am getting? See, after replacement of one of the hydrogen at this particular carbon, I am getting a stereo center. Now you can see this carbon is attached to hydrogen, attached to some group CH3, CH2, attached to CH3 and attached to some D. This carbon is chiral carbon. This was a chiral because there are two hydrogen atoms. No, what is chiral? When your carbon is attached to four different atoms or groups, then that carbon will be called as a chiral carbon, or molecule can also be chiral. But here we are talking about chiral center, chiral carbon. So this is a chiral carbon. And if I replace the other hydrogen, I'm getting again a chiral carbon. But what is the relation between now this compound and this compound? What you'll find, whenever you have prochiral center, this center is called as a prochiral. What is prochiral? Can anyone? What is prochiral? So prochiral carbon is something. If you replace hydrogen at prochiral center, you generate a chiral carbon. So this center, this carbon is called as a prochiral, or this is also prochiral. Okay. So prochiral carbon you are replacing one of the hydrogen by some other atom or group. Let's say D. Here also you are replacing the same thing. After doing that, now what is the relation between this compound and this compound? What you'll find here, D is beta, here D is alpha. So these two molecules are related to each other as enantiomers. What are enantiomers? Which are non-superimposable mirror images of each other. So these enantiomers are generated by replacement of these two protons. Then these two protons will be called as enantiotopic protons. So if you generate same molecule, then they are called as homotopic. If you generate enantiomers, then it will be called as enantiotopic proton. Now we cannot distinguish between enantiotopic and homotopic protons by using PMR. They will appear as single peak in PMR. So I will not be able to distinguish. Let's take another molecule now, another example. We have this example now. What is the difference now? Again, we have CH3, CH. Again, this is a prochiral center. Okay, just like the above example, this is also a prochiral center. But this prochiral is attached to a carbon which is chiral. Here, this carbon was achiral because there were two hydrogen atoms attached to this carbon. But here now you can see CH3, H and OH. So there is already a chiral center present in that molecule, and by replacing you will generate another chiral center. You can see here, now this is also chiral, this is also chiral, and this is also chiral, and this is always chiral. At the beginning only it was chiral. So by replacing now, you are generating two chiral centers. Initially there was only one chiral carbon. This was a prochiral center, and if I replace one of the hydrogen by some other atom or group, I am generating a molecule which will be related to this molecule as distereomer. What are distereomers? They are also stereoisomers, but which are not related to each other as enantiomers. They are not related to each other as non-superimposable mirror images. Then these two isomers, stereoisomers, will be called as diastereomers. So protons which generates diastereomers will be called as distereotropic protons. So environment of this hydrogen and this hydrogen, when you have a chiral center around it, is not same. They are different, and therefore we can distinguish between these two protons by using PMR. How they are different? So the dihedral angle will be different now. See this hydrogen, for example, in this molecule itself, you take this hydrogen and this hydrogen, which are alpha with respect to each other, they are syn. Whereas red hydrogen and the black alpha hydrogen, they are trans with respect to each other. OH relation. So dihedral angles are not same. If you draw a Newman projection formula, you'll be able to very nicely explain how these two protons are not same. The dihedral angle is not same. Now such kind of two protons are called as chemically equivalent but magnetically non-equivalent protons. Again, what do you mean by chemical equivalence and what is magnetic non-equivalence? Chemical equivalent means if I carry out some reaction over here, let's say I want to carry out a substitution reaction. If I carry out substitution reaction for this molecule, whether I replace this hydrogen by some X or whether I replace this hydrogen, red hydrogen by X, I get the same compound. I'll not get different compound. Then these two protons will be called as chemically equivalent protons. But, if I replace this hydrogen and get a molecule, what you'll find the dihedral angles of proton hydrogen and this D with respect to other groups are not same. Hydrogen and the D group, the dihedral angle with this other three groups are not same. We are talking about these actually, not about CH3. We are talking about OH, H and CH3. So if you draw a Newman projection formula between them, what you'll find that the dihedral angles are not same, and then such kind of protons will be called as distereotopic protons, as well as they will be called as magnetically non-equivalent protons. And we can always distinguish, we can always differentiate between magnetically non-equivalent protons by using PMR. They will appear as a different peaks in PMR. So very important that we can classify two protons which are maybe on the same carbon, but they can be homotopic, enantiotopic, or distereotopic. This is decided by the environment around them. If these two protons are present next to a chiral center, then these two protons will be called as distereotopic. If they are next to a chiral center, then if replacement test generates enantiomers, then they are called as enantiotopic protons. And if they are in non-chiral environment and replacement produces same compound, then they will be called as homotopic protons. So hope you understand what is homotopic, what is enantiotopic, and what is diastereotopic. So please remember, homotopic and enantiotopic protons will appear at the same peak. Will not be able to distinguish between them by using PMR. But yes, diastereotopic protons can be distinguished from each other by using PMR spectroscopy. Okay. So such two protons are called as chemically equivalent but magnetically non-equivalent protons. Let us take this example. You have a molecule in front of you. What you'll find, see here, these two protons are attached to same carbon, but they are non-equivalent. They will appear as a different peak. So for this molecule, we'll expect one, two, and three peaks. Okay, one for CH3, one for this hydrogen, and another for this hydrogen. Now, why these two hydrogens are giving two different peaks? Because we are in a rigid system. Cis bond rotation is not possible. This hydrogen is cis with respect to Br, it's trans with respect to CH3. The dihedral angle of this hydrogen with other groups is not same. Br and hydrogen, they are at 0 degree, whereas this hydrogen and Br, they are trans. They are at 180 degree, whereas CH3 and this hydrogen, they are cis, they are at 0 degree. So the dihedral angles are not same. Such two protons are magnetically non-equivalent and they will not be showing same peak. Their chemical shift will be different. Over here, what you'll find, this hydrogen is coming at 5.3 delta ppm, whereas this is coming at 5.5 delta ppm. So chemical shifts are not same because they are magnetically non-equivalent. These two protons will also be called as distereotopic protons because if I replace H by X, I'll get something else. If I replace H by X, I'll get different molecules. But those two molecules will be diastereomers, and therefore these two protons are called as a distereotopic protons. Now, not only chemical shift will be different, but these two protons will also couple with each other. So the distance between them is two bonds. So they will show geminal coupling between them. So remember, their coupling constant, their chemical shift will not be much different. Okay, very less different. So you can see a 5.3, 5.5 alipinic protons. Okay, so obviously value will be greater than 4.5. 4.6. So here you can say it is 5.3 because we have Br atom in the molecule. Chemical shift is very close, 5.3 and 5.5, very close. The difference is very less. So they will couple with each other by geminal coupling, and the spectra will be complicated because we will see the second order splitting in such kind of molecule, and the spectra will not be simple like a triplet or quartet, something like that. It will be different. For example, if I take this hydrogen, now this hydrogen is coupled with two types of protons. Hope you understand this. This hydrogen is coupled with this another hydrogen whose coupling which chemical shift is 5.5, and it is also coupled with this CH3, maybe 1, 2, 3, and 4 bond coupling. So a long range coupling of this hydrogen with CH3 will be seen, and a geminal coupling of this hydrogen with this hydrogen will be seen. As well as this hydrogen, no doubt is coupled with this proton, but also will be coupled by long range with this CH3. So now we will not simply calculate the splitting pattern by 3 and 1, 4 protons, and because we're not talking about here vesicular coupling, here we are talking about geminal and long range coupling. So the splitting will be by second order splitting and not by first order. Only first order splitting will be found out by using Pascal triangle, not the second order splitting. So what just now we spoke, that what do you mean by magnetically equivalent or non-equivalent protons. So you can see here that if the dihedral angle is the same, if chemical environment is same, then coupling constant values between them will be same, and those two protons will be called as magnetically equivalent. But if they are not same, one of them, even if I say not equivalent, they will be magnetically non-equivalent protons. Just now we have seen what is magnetically non-equivalent. Now this is simple CC bond rotation is possible over here. So we cannot distinguish. It's a flexi system. So these protons become equivalent in all respects. See here. These two protons are equivalent, or these two protons are equivalent. So they all are called as magnetically equivalent protons. So magnetically non-equivalent protons. Just now we are seeing the replacement test. If I have a molecule, this molecule is there. I'm replacing hydrogen by fluorine over here, and I'm replacing hydrogen by fluorine over here. Now these two molecules I'm getting. See here, NO2 and let's say fluorine, they are ortho with respect to each other. NO2 and fluorine, they are meta with respect to each other. So what two molecules I am getting, I and J, they are not same. They are isomers of each other, and therefore these two protons will be called as heterotropic. Now I'll not use the word stereotopic because in aromatic system over here, these two I and J are not related to each other as diastereomers. They're just isomers, structural isomers of each other. Therefore, these two protons will be called as heterotropic protons. So something which is not generating diastereomers but are structural isomers, then we will call it as a heterotropic proton. So homotopic, heterotropic. Homotopic means same molecule will be obtained. Heterotopic means two different molecules will be obtained, but they are not related as enantiomers or diastereomers. Then we call those two protons as heterotropic protons. So this is another example of magnetically non-equivalent protons. So for example, over here, I have a molecule, okay? Para-nitrochlorobenzene is there. What do you find? These two set of protons are equivalent. These two protons are equivalent. Their chemical and magnetic environment is same. Therefore, they will appear as the same peak. So you can see here 7.63, 7.63, 7.99, 7.99. So these two are different, but these two are same because their environment is same. Now, why this hydrogen is coming at 7.99 and this is coming at 7.63? One is more de-shielded than the other. Both are de-shielded. Let me tell you, normal benzene proton will appear at 7.25. Any delta value for aromatic proton greater than 7.25 will be called as de-shielded. 7.25 will not be called as de-shielded. It's a normal aromatic proton. Any value less than 7.25 will be called as a shielded aromatic proton. Greater than 7.25 will be called as de-shielded aromatic protons. Since both are greater than 7.25, will be called as de-shielded aromatic protons. But X is more de-shielded than A because its chemical shift is greater than A. Can you tell me why HX is more de-shielded than A? You see, look at the molecule and you can write in chat box, you can unmute if possible and let me know why X has more delta value as compared to A. Yes, anyone? Are you there with me? Yes? Yes, anyone?
Yes, madam. Chat box is open.
Okay, so you can see the molecule. What you'll find, we have a nitro group in this molecule. Nitro is highly electron withdrawing and it is ortho with respect to HX and it is meta with respect to HA. Now you know electron withdrawing minus R effect is observed at ortho and para positions, maximum at ortho and then para, because at ortho we also have minus I and minus R. So you can see HX, which is ortho with respect to NO2, faces both minus I and minus R effect. So both are going to increase the delta value. It comes to 8, approximately 8. Whereas A is meta with respect to NO2. No doubt it is ortho to Cl, but Cl has less electron withdrawing as compared to NO2. Therefore, it comes at 7.63. No doubt impact is there of Cl, but NO2 has maximum impact. Therefore, the HX is more de-shielded as compared to HF. So these two protons will couple with each other. What kind of coupling will be there? 1, 2 and 3 bond coupling. But over here we do not call it as a 3 bond coupling. Here we call it as the ortho coupling. So in case of aromatic system, we'll call it as the ortho, meta or para coupling, out of which meta and para are long range coupling, whereas ortho is a it's like a 3 bond coupling. Okay, so the value will be around 7 to 8 hertz. Normal your vicinal coupling. It's like a cis coupling. Okay, you can see HX and HA are cis with respect to each other. They're at 0 degree. So value of cis coupling and ortho coupling is very close, but we have electron withdrawing group along with that. So the value will be less compared to cis coupling, and these two will appear as doublet. Another molecule, here you can see these two protons are magnetically non-equivalent. These two protons are magnetically non-equivalent. This is because we see the environment around them. If you replace hydrogens by some X, you'll get diastereomers, and that is why we are calling them as magnetically non-equivalent protons. You take alene type of system, again these two protons can be distinguished by using PMR. They are magnetically non-equivalent. See the beauty of NMR spectroscopy, that we can distinguish between these two protons, these two protons, these two protons, which was really very difficult otherwise. If you carry out a chemical reaction, we cannot distinguish between them. Here also you can see these two X hydrogen atoms, we can distinguish between them if the coupling constant between HAX and HAF, whatever it is, it's a fluorine, okay? But you know that fluorine also get coupled with hydrogen. So the coupling constants are not same. We can distinguish between them. They are all called as magnetically non-equivalent protons. So how the spectra will become complicated now. After first order splitting, now we are talking about second order splitting. So if I take this hydrogen, no neighboring proton will appear as a single line singlet. Okay. Now you have a hydrogen which is coupled with another hydrogen. So there are two, these two hydrogens are coupled with each other. You will see a doublet, and the distance between the two lines of the doublet will be called as a coupling constant. So this is how it will look like. Now we making the molecule more complicated now, okay? On the same carbon, now we are increasing one more hydrogen. Now this hydrogen, we are talking about blue hydrogen, okay? Coupling of blue hydrogen in that molecule. How it will appear? Here it was singlet because no neighboring proton. Here it is doublet because there is one neighboring proton. Simple n plus 1 rule, three bond distance, vicinal coupling, done. Now here we'll go. These two protons, A and B, are not equivalent. They are magnetically non-equivalent because we are talking about a rigid system and the dihedral angle of A and B with other atoms is not same, so magnetically non-equivalent proton. So your hydrogen will couple with B and your hydrogens will couple with A. Now the coupling constant will not be same even the distance is same. This is because dihedral angle is not same. H and HB, the diagonal angle is 0 degree, they are cis with respect to each other. H and HA, they are trans, the diagonal angle is 180 degree, approximately 180 degree. So diagonal angle is different, coupling constant will also be different. Karplus says that dihedral angle changes, the coupling constant will also change. So what you will find? The coupling between cis protons will be less as compared to coupling between trans protons. So now your two lines will become four lines and they will appear as a doublet of doublet. Now, I am not calling this as a quartet. If you remember, Pascal said that if there are three neighboring protons, then it will appear as a quartet in the ratio 1 is to 3 is to 3 is to 1. But here we are not talking about it. Now here we are talking about second order splitting. That first doublet will take place because of HB, because of HA, and that doublet will be further split into another doublet because of coupling between HB, and this is how the doublet of doublet will look like. So you can see here that there are four lines, one, two, three, four, and it will look like a doublet of doublet. So this language you need to understand now in case of second order splitting. So you take your hydrogen and it will first split into two lines, and each line of the doublet will become again further splitted into two lines. So the coupling between J, H and B is less as compared to H and A. Therefore, first splitting will take place because of a trans coupling. The distance between these two lines is greater than these two lines because the coupling constant of trans is greater than cis. So this is how the doublet of doublet will look like. And if I increase one more hydrogen, 1, 2, 3 bond coupling again with HC, it will look like doublet of doublet of doublet. Three doublets will be seen if there are three protons coupled, all are coupled by three bond coupling, okay? There is no geminal, there is no long range. All are 1, 2, 3 bond, 1, 2, 3 bond, 1, 2, 3 bonds. This three bond is called as a cis coupling. This three bond is called as a trans coupling, and this three bond is called as a vicinal coupling. Each proton will split line into two lines n plus 1, n plus 1, n plus 1, 1 plus 1, 1 plus 1, 1 plus 1. So 1 plus 1, two lines, two lines, two lines. So doublet of doublet of doublet, and this is how the DDD 6 lines will be seen. See, sextet is different. The intensity ratio will be different. Over here, all will have same intensity, they'll be of same height, but the distance will be different because three coupling constants are different. What you'll find that the highest coupling will be between A and H, so the highest distance. So if I want to find coupling constant, difference between first and second line will give me the coupling between H and this HC, that is vicinal coupling. Distance between the first and third line, you can say, will give me the or this thing, the cis coupling, and the distance between the middle of these two doublet, and middle of these two doublet will give you the distance with the coupling constant between H and A, that is transcoupling. So this is how a spectra becomes complicated when second order splitting is observed. When second order splitting is observed, so second order splitting is observed when you have uh, magnetically non-equivalent protons next to the proton. At that time, you will see a complication of spectra, and this complication of spectra will be observed based on how many types of protons are next to it, what is the dihedral angle, what kind of coupling exists between them, what is the distance between these two protons. All these factors will decide the value of coupling constant, and that will decide the splitting pattern of that proton. Hope you are understanding what we are talking about is it about the second order splitting. Any doubts? Can you type in a text box, chat box? Is it possible for you?
Is there any doubt? Please
No,
ask.
not. I think you can't type anything or you can't speak. So fine. Uh, so um, these are the things we will look at when we talk about PMR spectra. That how many signals, what is the position, what are the relative intensities, and what is the splitting pattern. All this information once I gather, I can read the NMR spectra. So I have to understand the language of spectroscopy, what these values on x-axis indicate, what the height of the peak indicate, what the lines, splitting of the lines indicate. Once I understand this, it becomes very easy to interpret the MR spectra. So some of the examples I've shown you that this is how the spectra will look like. So we will talk about coupling cost. Sorry, we will talk about the chemical shift. We will talk about the splitting of lines. We'll talk about the number of peaks. We'll talk about the distance between the splitted lines. All this information is very important when we talk about a interpretation of the spectra. So you can see here See here, there are one, two, and three types of protons, out of which A and B are aliphatic protons and C are aromatic protons. A type we have six protons, B type we have four protons, and C type aromatic we have four protons. Out of these, your C type of protons will have highest chemical shift because they are aromatic protons. There will be normal aromatic proton around 7.2 because CH2 ethyl group does not have much impact on benzene protons, aromatic protons. Now CH2 and CH3, these two are coupled with each other, and CH2 will be more deshielded than CH3. One, it is highly substituted carbon as compared to CH3, and it is next to aromatic ring. So both will have impact at a value around 2.5, and it is appearing as a quartet. Simply a Pascal triangle says 1 is to 3 is to 3 is to 1. The quartet will look like this. If the intensity ratio of the lines is not 1 is to 3 is to 3 is to 1, then it is second order splitting. If it is, then it is quartet, and it is quartet because next to that there are three protons, neighboring protons, so 3 plus 1, 4 lines. If I take CH2, sorry, if I take CH3, next to that we have CH2. Obviously, CH3 proton are more shielded as compared to CH2. The value will be around 1.1 or so. And it will happen as a triplet because there are two neighboring protons to CH3. So by your n plus 1 rule, 2 plus 1, 3 lines, 1 is to 2 is to 1 will be the intensity ratio. And this is how the spectra will look like. Very simple spectra. Another example is there that you have di and propyl ether. What you'll find there are again three types of protons, six A type, four B type, and four C type of protons. Here, oxygen Region is directly attached to CH2, so these are the most de-shielded, highest delta value. And next to CH2, therefore, appear as a triplet. You can see the triplet at about 3.5. You'll see this triplet for C type of proton. For A type of proton, again it is next to CH2, so you'll find that around zero point 0.9 you'll see a triplet due to presence of this CH3 next to CH2. Now let's take CH2. What you'll find as the chemical shift difference between AB and BC is quite high, we'll not see the second order splitting, we'll see only first order splitting. Now what is first order splitting? Just count the number of proton next to it. So there are 3 plus 2, 3 plus 2, 5 protons, A3 and C2, 5 plus 1, 6 lines will be observed. So you can see here 1, 2, 3, 4, 5 and 6 lines. It's a simple sextate will be observed for B type of proton. So the first order splitting spectrum will look like this, and it is not very complicated, very easy to interpret. Another example is there, the 9 hydrogen which are equivalent. See the height is very high, density is very high, integration will be of 9 hydrogen. Then you have a CH2 which is next to aromatic ring, de-shielded. So you can see here, these 5 protons, aromatic protons, monosubstituted as benzene ring, 5 protons will not have same chemical shift, very close chemical shift. Therefore, clustering is observed, and that clustering is around 7.25, and therefore the broadening of the peak, aromatic protons peak will be observed, but not because anything else. It is just because the chemical shifts are so close that they are getting merged with each other, and that is why it is looking like a broad peak. There is no other reason otherwise. So, in case you have the molecular formula, you can always distinguish, you can always predict the structure of the molecule if you know the spectral values. Okay, so let's say we have the spectral values. For example, we have 6 hydrogen which appear as a singlet 1.57, then another 2 hydrogen peak is there which again appear as a singlet with 3.07, and there are 5 hydrogen at 7.25 27. 7.27 indicates they are aromatic protons. 5 hydrogen says that it is monosubstituted benzene ring. So out of 10 carbon, 6 carbon already you have assigned for a benzene ring. Now how many carbons left? 4 carbons left. Okay. Out of 13 hydrogen, 5 hydrogen belongs to your aromatic ring. Now, any signal where 2 hydrogen equivalent, generally it is CH2, and if there are 6 hydrogen, then there can be 2 CH3 or 3 CH2s. So, we can roughly write about after looking at these peaks. Now, all are singlet. What that indicates? That they are not coupled with each other. They are not next to each other. Whenever you have a molecular formula, you generally find out the what are the sites of unsaturation, or we call it as degree of unsaturation. Du, degree of unsaturation. Su, sites of unsatuation, one is the same. What is the formula to find degree of unsaturation or sites of unsaturation? So number of carbon atoms into 2 plus 2 plus number of nitrogen atom minus number of hydrogen and halogen atoms. Okay, this is the formula divided by 2. So please remember this formula. Any organic molecule you want to find out how many double bonds or how many rings can be present, we have to find out how many sites of unsaturation or degree of unsaturation present in that molecule. So degree of unsaturation or sites of unsaturation are calculated by using this formula, that is 2C means number of carbon atoms into 2 plus 2 in plus n number of nitrogen atoms minus number of hydrogen and halogen atoms. This will help you to find out the sites of unsaturation or degree of unsaturation. So what you'll find the degree of unsaturation, let's say for this molecule I want to find out. So 10 into 2, 20 plus 2, 22. no nitrogen, minus 13 and this chlorine, 14. So 22 minus 14, how much it is? 8 divided by 2, 4 sides of unsaturation, and generally 4 sides of unsaturation are for aromatic ring. So already we have confirmed that there is aromatic ring which is monosubstituted from PMR. So we can draw the structure now in permutation combination. You have to see such that these two protons will not be next to each other because all are appearing as a singlet. So I can here write more than one structure, but I have to assign one structure for the given data. So I can write this CH to this side and make things different. Okay, structure can be possible, but then when I look at the splitting pattern, singlet, 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 it indicates that this has to be the structure of the compound. So from the given data, from the spectra, we should be able to draw the structure of the molecule, or there is a structure in front of you, you should be able to predict how the spectra will look like. So both things are possible and one can do it. Now, on the basis of splitting, we can classify coupling system on the basis of their spin. So, if there are two protons which are coupled with each other, then they will be called as AB or AX system. If there are three coupled protons, then you can call it as the ABC, AMX, or XYZ system. So, what is this nomenclature system for coupled protons? So, obviously, those protons which are chemically equivalent cannot be distinguished from each other, so they will be designated by the same alphabet, either A, B, or X, or M, N, something like that. Now, how do I decide whether to write A, whether to write M, whether to write X? It is decided by the coupling constant, sorry, the chemical shift difference between the two protons. If the chemical shift difference between two protons is very high, two protons which are coupled with each other, if very high, then we designate it as a AX. In alphabets, A and X is very far from each other, right? And A and D are very close to each other. Or A and M having moderate distance. AX is very far, AB is very close, M is moderately close. So, two protons, if their chemical shift difference is very high, then they will be designated as AX system, and their chemical shift difference is very less, then they will be designated as AB system. So two protons when coupled with each other, two spin systems will be classified as X or AB on the basis of whether the difference between two coupled protons, the chemical shift difference is very high, then X, if chemical shift difference is less than AB. Now, what happens if you have a different spin system? The spectra looks very different. Okay, let us take AX system, nicely separated two doublets you can see. See, for A there is one doublet, for X there is one doublet. Now these doublets are at very high distance, okay? They are very much away from each other. Why? Because their chemical difference is very high and it is more than 5 joule, or you can say the distance is very high. Therefore, the well separated two doublets will be observed. But in case if they are very close and the distance or the difference between delta value is less than 5 hertz, then what you will find that these lines, first and the fourth line, or the lines of the doublet, they are reduced and the middle line intensity increases. This is called distorted doublets. Okay, this is not cottage. This is doublet, but it is called as distorted doublet. So AB system doublet will look like this. AX system the doublet will look like this. In doublet, the two doublets are not in 1:1 ratio. The inner lines are larger than the outer lines. So this is how AB system doublet will look like. And this is how AX system doublet will look like. If you have a three spin system, And they can be classified as AX2, AB2. What is AX2? AX2 means we have one proton of one type, A type, and there are two protons of X type. So there are total three protons, out of which two are X type and one is A type. Then that system will be called as AX system, AX2 system. How the A will appear? 2 plus 1, 3 lines. The triplet, and how the X will appear? A is only one type, one proton, A type proton, so it will appear as a doublet. So doublet and triplet will be observed from A and X. AB2 again same. Now why AB2? What is the difference between AX2 and AB2? The chemical shift difference when very high, AX2. Chemical shift difference is very poor, then AB2. Both should uh, split as a triplet and doublet, but AB2 distorted and shows like a second order splitting, whereas AX2 will show very nicely separated a doublet and triplet will be observed. This is here. This is the AX2 system. X will appear as a doublet, nice doublet is there, and A will appear as a triplet, so nice triplet is there. This is when two protons have high difference in their chemical shift. But if two protons are very close in their chemical shift, take this one, two, and three protons. This is again a three spin system, but it is AB2 type. This is if this is A, these two are B type of protons, so AB2 system. Now see here, AB2 is so complicated and not appearing as a doublet and triplet. The lines are very much distorted. So what you see that there will be a second order splitting and like a doublet of a doublet they will start appearing. So you can see here, it's like a doublet of doublet. This is also doublet of doublet. So complication will start, or doublet of triplet will be observed. Complication will start once two protons, any two coupled protons, their chemical shift difference is very less, then you will see a second order splitting. If the chemical shift difference is high, then nicely first order splitting and nice separated quartet, triplet or triplet doublet will be observed. So three spin systems it can be classified as AMX, ABC, or AXY, something like that. You can see here, when we have three protons coupled with each other, A will appear as a doublet of a doublet, M will appear as a doublet of a doublet, and X will also appear as a doublet. What this AMX indicates? That delta A will be always less than delta M will be less than delta X. X is something whose chemical shift is high, M is a moderate chemical shift, and A is a shielded proton or the chemical shift is less. You can see this is also doublet of a doublet, this is doublet of a doublet, and this is also doublet of a doublet, depending upon JAM, JAX, and JMX. What are the values? We can see this type of doublet. But the moment I change system from AMX to ABC, you can see the distortion will be seen. Second order splitting is there, along with that distortion will be there because there you can see here now C. ABC. So C again doublet of a doublet, B doublet of a doublet, and A also doublet of a doublet, but not very clear, very much close clustering, and the intensities of the outer lines decrease and the inner line goes on increasing. This is how the complication of the spectra takes place as per the spin system. See here, ABX system, ABX, CX, chemical shift is very high, it's well separated doublet of a doublet, but you see the AB system, the doublet of a doublet is not clear, very complicated because chemical shift difference is very less between A and B. So in the general, two spin, three spin, and four spin system can be represented in this manner. They can be classified as AX3 or A2X2 or A2D2 or AB3 or A dash, B dash, depending upon what is the chemical shift of these protons and how many same type of protons are present. our four spin system can be classified in various ways, and this is how the moment you go to A to B to system, spectra becomes more complicated. A to X2, you can see now the triplet of A and triplet of X, so nicely presented, nicely separated. But AB3 or system, you can see it is complicated. A dash, B dash, very close chemical shift, so very distorted spectra is there. AX3 spectra is good. AX3, see one quartet and one doublet. A will appear as a quartet because there are three same type of proton next to it, whereas your X will appear as a doublet because there is one proton of A type. So doublet quartet pattern is there. First order splitting because A and X chemical shift is very high, difference is very high. But the moment you go to A to B2, still it is better. But A2X2, still it is better. But A2B2, AB3, they have very complicated spectra because their chemical shift. So nature of spectra is also decided by the ratio of delta mu by J. If delta mu by J ratio is poor, is less, then the spectra becomes complicated. In case of AB systems, in case of AM system, the spectra is complicated. But AX spectra is good. It's first order splitting, nicely well separated. Peaks will be observed. So this is about your H1 NMR. Now, see, we our topic is NMR. Now, either I can go to C13 NMR or I can go the simplification of H1 NMR. So right now I'm not, I don't know whether we'll be meeting again, whether our lecture will be there or not. But roughly I'll just stop. Just now we spoke about H1 NMR, and there is another NMR, that is C13 NMR, which is again equally important for us to get the structural information about the molecule. There is big difference between H1 NMR and C13. As I told you, C13 carbon exists in C12 form in 99.9%. The percentage abundance of C13 is very poor. Therefore, what you need, very high power instrument is required to detect C13. The chemical shift range for hydrogen, it was only 0 to maximum 12, 13. But in case of CMR, the chemical shift range is very high. It is from 0 to 200 delta ppm. Splitting pattern in case of H1 hydrogen, it was because of neighboring protons or long distance protons, like your long range coupling, or it can be a two bond coupling also. But in case of carbon, we can have a splitting because of carbon, which is directly attached to hydrogen. Splitting is maybe because of that, or it can be C13, C13. But as you know, there is very poor percentage of C13. And next to that, two C13 coming close to each other, neighboring to each other, is again very rare. So most of the time, C13 coupling is not observed, but C13H coupling is always observed, and one can find out the information from it. The value of coupling constant between carbon and hydrogen is very high, from 100 to 250 sorry, 100 to 250 hertz, which in case of hydrogen it is very less. So these are the major differences between PMR and C13 NMR. C13, first thing, the instrument, highly powerful instrument is required because we have very less percentage of C13. C12 we cannot detect because I value is 0. Magnetic spin quantum number is 0. And if I want to detect C13, problem is that uh, poor percentage of C13. Splitting pattern, as I told you, that is because of generally C13 hydrogen and not because of C13 C13 coupling, very rarely observed. Intensity in hydrogen in PMR was because of the number of equivalent hydrogen, but in C13, intensity is decided by two things. One, how many equivalent carbon atoms are there, and how many hydrogen atoms are directly attached. So what do you say? The integration does not give much information about the number of equivalent carbon like hydrogen. It is not that authentic because there are two factors which decide the intensity in CMR, which is not decided in H1NO1. See here, we have sp3 type of carbon, we have sp2 sp type of carbon and you have sp2 type of carbon. So this is how roughly the chemical shift changes up to 210. The most deshielded is ketone or aldehyde carbon. Then we have carboxylic acid, amide, esters, and then all these are sp2 carbon with heteroatoms. Then you have benzene ring carbons from 110 to 160. Then you have olefinic carbons 100 to 150. Yeah, alkyne 65 to 85. Yesterday we spoke the chemical shift is in between sp3 and sp2 because of the anisotropic effect. And then your aliphatic carbon will be up to 80 delta ppm can be observed, and this is how the CMR delta values will be there. Again, here TMS is used as an internal standard, and most of the time silicium is the solvent, which is delta value is 77. You can understand there are three chlorine atoms, so it will appear. It will come at about 77 delta ppm because of three Cl atoms. This carbon will be highly shielded. But it appears as a triplet, and you can find out easily that solvent peak can be easily detected. As I told you in H1NMR, deuterated solvents are used because we cannot see their peaks. But in now in CMR, you are going to see peak because we are not talking about proton, we are talking about carbon. We will see the peak, but this peak will be totally different from other peaks because here we have a deuterium. 2Ni plus 1 is the formula to find the splitting pattern. I value is 1. So 2 into 1 plus 1, 3 lines, triplet of equal intensity, 1 is to 1 is to 1 will be seen. And at 77, you can easily distinguish the solvent peak. So here, generally, ClCl3 is used as a solvent. As I told you, integration is not like H1NMR, where we can find out the number of equivalent protons. In C13, integration is giving information about the carbon, equivalent carbon, as well as number of hydrogen atoms directly attached to carbon. Also decide the intensity. The relaxation time is decided. The carbon when undergoes excitation and de-excitation. The relaxation time is decided by number of protons attached also. And therefore here integration does not give information about the equivalent carbon atom. We might get little bit information but not authentic information about the integration. So this is how the difference between H1NMR and CMR will be seen. Now if we get time sometime, then we want to talk about what are the different methods to simplify the spectra and what is 2D NMR spectroscopy. Let's see what happens. A little bit about depth and decoupling experiment in CMR and the 2D NMR as well as simplification techniques of NMR can be discussed after this. Let's see if time permits. Surely we will discuss about it. Now, as I told you, that you may have some difficulties in what we spoke, or you may have some queries. So I would like you to just note down my email ID, so you can always mail me and ask any question related to what we have done, and obviously what something which we have not done also we can discuss. So my email ID is given. manishabora@gmail.com. You can always contact me on this Gmail ID, and I will be very happy to answer your queries because we couldn't find time, or maybe the system is such that we can't interact. But that's fine. We can always interact on email. So whatever we have done, hope you have understood. Hope you have enjoyed the lecture. And if you have any queries related to this, kindly give feedback on my email. I have shared my email ID. And if time permits, we surely talk about how to simplify NMR spectra and 2D NMR spectroscopy. So with this, I'll stop here. Thank you so much. In case you have anything, let me know. Hello.
Is there any questions? Please ask. Am I audible?
So
Yes, sir,
if
you
you
are audible.
put anything in the chat box, if you have any query,
Yes,
we
yes.
still have 10 minutes. We can always discuss. If you have query, if you don't have, I've given my email ID. You can always discuss about that. In case if you want us to discuss about the this thing simplification of and 2D NMR. Surely we will have one lecture based on that. Thank you. Is there any faculty over here with us?
Okay. Now is the time to give vote of thanks.
Nitin sir?
It is my pleasure. Hello, madam.
Hello?
Yes, am I audible?
I think student can't speak or they can't type in chat box. That's what
Ah,
the
yes,
system
yes.
is not allowing them to. Yeah. Am I audible?
Yes, yes, yes. So is now the time to give vote of
Okay,
thanks.
I'm getting answers. Fine. Fine. Okay, fine. So shall we stop here?
Yes, yes, yes.
Nitin sir?
Yes, yes, yes. It is my pleasure to deliver the vote of thanks on this special session. I extend my heartfelt gratitude to our today's second section resource person, Professor Dr. Manisha Bora, madam, for taking time out of your busy schedule to be with us. Today, madam explains splitting pattern, coupling constant, homo topic, enantiotopic, diastereotopic protons concept, various shades